It's time for pure performance.
Get your stopwatches ready. It's time for Pure Performance with Andy Grabner and Brian Wilson. Hello, everybody, and welcome to another episode of Pure Performance. My name is Brian Wilson, and as always, I have with me my wonderful co-host, Andy Grabner. How are you doing today, Andy?
Pretty good. It's I think we both survived Halloween, huh?
We did both survive Halloween, and today's already off to a good start. If you know, you know. I'll just leave it at that.
Yeah. There we go.
Yeah.
But how was your, everything good? No, I think you told me that you bought too much candy.
Well, yeah, we usually, so we're on like this weird half crescent street with no street lights, but a lot of the people have like Halloween lights up and stuff. And also we try to, sounds terrible, we try to lure kids to our houses with candy. Boy, I never thought of Halloween that way. But either way, you know, we just didn't have a high turnout. But last year I started buying, you know, the large candy bars, which was always like the goal, you know, the holy grail for as a kid. And yeah, we just didn't have too many this year. So I have a bunch of leftover large candy bars that I'll get to eat myself. So I guess it's a win-win, you know?
Yeah, and I think also because you didn't have too many kids, it was not too chaotic. You didn't have to deal with two chaotic situations in front of your house, kids fighting for candy. What do you do if you run out of candy?
I have to come up with a hypothesis first, yeah.
I think so, yeah.
What happens if the chaos is in my house? What if I ran out of candy? What would I do if I ran out of candy and had none? Yeah, a lot of things. Yeah. Andy, this is fantastic. A lot of things can happen on Halloween, and you got to plan for all of them, right?
Yeah, and as Halloween is over, also our jokes are now over because it's about time to introduce our guest. Bartek,
did our jokes ever happen?
Bartek, thank you so much for being on the podcast today. Sorry that you had to go through 1 or 2 minutes of the two of us trying to be funny, but we also try to always do a little bit of a segue to the topic, which means today we're going to talk about chaos engineering. Bartek, please do me a favor, introduce yourself, who you are, what is your background, and also what excites you about chaos engineering.
Of course, and thank you for having me. By the way, I think that Halloween is a great introduction to chaos in general. So I think it's a really good start. So my name is Bartek, and I'm working right now at Pegasystems. My responsibility is for the overall quality of our cloud infrastructure. So this is what I do with my team. And of course, if you think about quality, it's a very broad term, and you can think about the technical quality, but it's not everything. It's also about documentation quality, process quality. So basically, there are a lot of things that you can put under the umbrella of this single word. Right now. And why I'm really interested in chaos engineering topic, and this is something that I've been exploring for a couple of recent years, and I've been giving different talks and different conferences about chaos theory and chaos engineering. Right now, in the modern world, when you have enterprise systems, which are basically a set of different microservices or services working together, any failure introduced to that complex system can cascade and can cause unexpected problems everywhere. And this is a technical side of chaos engineering and chaos theory in general in IT aspect. But also, if you think about small things like how the fact that you had a great party last night as a software engineer can affect the quality of your code, which then can eventually can lead to cascade problems on production. So this is another aspect of chaos theory in the context of IT. And we saw great examples recently with AWS issues. That was, I think it was last week, if I recall correctly. Azure had recent issues. So all of that is just a business justification for really, really playing with chaos engineering and really having it and embracing in different parts of organization.
I have a question now. Do you think a valid chaos experiment would be to organize parties in the middle of the week with a lot of alcohol and then see what happens the next day?
Oh yeah, it sounds like a great plan. I don't know if you're aware of this. I think it's called a Bilmer's peak, if I recall correctly, which is correlating the level of alcohol in your blood with the quality of the code that you can produce. And there's this small peak of product, which is the highest productivity. So it might be pretty interesting, to be fair, to have something like this.
So wait, there was a study that said like at a certain level of alcohol, you're going to have better code. And then after that, you break the threshold.
Yes, but the peak is it's very like little. A very small range, where you can hit the peak, and all of a sudden after that, it goes down sharply. So
I just want to make sure, listeners, we are not encourage you to now start drinking and then writing production code or automation that is doing things. So please stay sober.
Especially with all the beer in all the offices, no one's encouraging you.
Yeah. Now to a more serious note, Bartek, I saw you at Cloud Native Days Austria. It was really good to have you co-present, and you talked about you gave a lot of background information about chaos theory. You gave a lot of basic information about also, or introductory information about what is the general test cycle, software delivery life cycle, where does chaos engineering fit in. So folks, if you're listening to this and you would like to see a good introduction about chaos engineering, we'll definitely have the links ready for you in the podcast summary. For me, what I would like to know a little bit more, especially for those that may have listened also to some of our previous podcasts on the topic, even though the last episode has been, I think, at least 2 or 3 years ago. How has chaos engineering changed over the last maybe year or two, especially with AI? Because you also brought up in your talk, right, the chaos engineering with AI. Do we see benefits? Like where can AI really help us? In which aspect of chaos engineering?
That's a great question. And before I answer directly in the context of chaos engineering, I would like to start with the statement that AI is changing and shaping our industry right now, including chaos engineering as well. And something that I was presenting during my presentation, one of the slides, or I think I don't have it, to be honest. I had it in my different presentation, but you can easily Google something that is called the Gartner Hype Cycle. So in short, the Gartner is the company that is providing information about how different technologies, how mature they are right now. And this is source of knowledge for different companies to really follow the specific trend that is right now on the market or not. And one of the concepts that they have is exactly the hype cycle, where they take a look at where the specific technology on the market is and how mature it is. And if you look at this chart that they have provided, for most of new technologies, you see the hype, then you see the peak of the hype, then you have the moment when the hype is going down, and there is the moment when the market is saying, okay, now show me real tools that can help to drive my business forward so I can really get an advantage. And if you look at the current Gartner hype cycle for generative AI, and you look at different areas that are related to AI, you can see that most of them are actually started entering the stage where market really wants to see tools that people can use to generate the value. And this is where we are. So the second thing that is related to current revolution of AI is that we are seeing more and more companies that are actually introducing different products and different technologies, which are speeding up their processes, automating their processes, boosting productivity. And there are different surveys that are saying that some percentage of people who are not embracing or using AI to boost their productivity is actually going to be laid off. And we are seeing that on the market. One of the research that I'm using in one of my presentations is saying that in 2025, 35% of business leaders are saying that AI will replace employees at the companies. But on the other hand, the same people are saying, and it's 9 in 10 companies, that they're going to be hiring people with AI skills. So on the one hand, those people who are not following, who are not learning new stuff, yes, they can be worried. But at the same time, it's not about laying off people. It's about boosting productivity. And there is a smart quote that from Jensen Huang, who is the CEO of NVIDIA. He said something really smart that I'm trying to convey in almost every discussion that I have about AI. He said that AI is not going to take your jobs. The person who uses AI is going to take your job. So that's basically the summary. So whether we like it or not, AI is there. We may not be thinking that it's a silver bullet for any problem, for solving all the problems. But at the same time, if you don't want to stay behind, you just have to embrace the fact that it's there and play with it and try to see how it can help you, boosting your productivity. So jumping into chaos engineering itself, as any other area of IT, it is also affected by the fact that we have artificial intelligence, and we have all those great things that especially generative artificial intelligence. So what I'm observing is that, as in every other area, we're seeing more and more proof of concepts, more and more people playing with AI. In different contexts of chaos engineering, chaos engineering steps that you're normally doing when you think about performing an experiment. And something that I was focusing on during the presentation are those 5 steps of doing an experiment. So you have the definition of steady state, you have the hypothesis generation, running experiment, verifying and improving. And in every single of those stages, you can actually think about using artificial intelligence to boost the productivity and to speed up the entire cycle and to get better results.
Mm-hmm. Cool. Thank you so much I took down the note, by the way, or the quote from the CEO of NVIDIA. I think it's definitely a great reminder that as the industry is changing, we just need to make sure we learn the latest trades and the latest tools. Because, as you said very nicely, right, AI is not going to take your job, but the person that knows AI better than you may kick you out of the job. And so you need to step up. So we all should experiment with it. Coming back to chaos engineering, practical examples in these 5 steps along that life cycle, where do you see the biggest change also in the way you run chaos experiments? Where have you seen the biggest impact in terms of you leveraging AI for the hypothesis generation, for the load generation, for enforcing chaos? Let us know where should people focus on as well?
Yeah, sure. So we can go one stage by another, and I think that would be the best way to actually describe what I have in my head right now. So let's start with definition of steady state. And definition of steady state usually requires some kind of observability tool to be applied to the specific system. So you can basically identify, first of all, which metrics you should observe, which metrics are actually defining your steady state. That's the first step. The second is to make sure that you can clearly say in which ranges the specific metric should stay to be able to say, hey, this is my steady state. Yeah. And normally what is happening, if you try to detect if you're out of steady state, is that you have some threshold. Yeah, it can be low threshold and high threshold. And if the specific metric is above or below, then some kind of alarm should be triggered. Now, what is really helpful in the context of implementing AI for that kind of observability model is that AI can actually learn from the past experience and from the past data and can trigger different kind of alarms way faster comparing to just setting the threshold. So let's imagine that this response time of one of your services and one of APIs that you have exposed, it's, set to 200 milliseconds or something like that. This is your high threshold. And you have to wait until this is really happen. If this is higher, then you're going to get an alarm. Now, if you can feed your model with any data from the past, with some patterns, observations, the model can actually learn behaviors. And if it's going to detect that the specific metric is going up and the pattern is something that happened in the past that can lead to failure of your system, it can trigger alarm way sooner than reaching those 200 milliseconds, because it can trigger an alarm, let's say, around 100 milliseconds or something like that. So you just don't waste another time to react. So that's the one of the things that you can actually implement and use generative AI, not only for chaos engineering, but also for observability and alerting in general.
Yeah.
Right. So for that one, it sounds like, and I'm not here to talk about Dynatrace in any way, shape, or form, right? But we've always done the baselining of the data, and we're looking for a variance in the baseline. It's not saying we're not setting 200 milliseconds. It's like, this is your normal state. If you vary 5%, 10%, whatever the defaults are, throw the alert. That's the starting point, right? But what you're looking at, what you're talking about, is looking for patterns, right? So let's say you have a response time starting to climb, right? But it hasn't violated your baseline yet. But at the same time, you see, maybe it's a response time on a service, but at the same time, you see a response time maybe on a database starting to climb, right? That might indicate, and neither of them are violated. But if the AI recognizes that pattern from a problem in the past, it's not just going to say, well, you haven't violated yet. I'm like, oh, I'm seeing this pattern again, right? Which makes the analysis, at least from the human point of view, more complicated, right? But if I understand what you're saying, the AI can look for these patterns it's learned in the past to say, if A plus B equals X, then I know we're going to have that problem. Whereas in the past, it was just, if A is going off, I'm not going to say anything until it reaches that threshold. Is that a correct understanding?
This is exactly what I'm talking about. And AI is great with finding patterns. Yeah. And AI is great in finding patterns using large data, large amount of data, which is pretty hard for people to do.
Yeah.
So that's the beauty of implementing AI in this context. But this is exactly what I'm talking about here.
So, but and maybe a last word on this. For me, this seems like a combination, Brian, as you said, right? Because the baselining or understanding what is the normal behavior of every individual metric, this is something where we don't need to throw an AI algorithm on it. This is classical statistical means of defining what is a baseline. The real interesting thing is then to look at historical data and understand if 5 different things behave in a certain way, then we know from history that something bad is going to happen, most likely. I mean, we at Dynatrace do this through our Smartscape and the way we analyze the data. And obviously, if you're putting all of your observability data into an AI nowadays, you can probably also get into some of this better behavior. I think that's nice. Yeah, that's a cool thought.
It also helps out a lot more with predicting earlier. Right? As opposed to, it's like, as soon as we start seeing the signs of that pattern, maybe it doesn't do a high level alert, but maybe it's like patterns starting to happen, right? It's awesome. I think the pattern, again, we talked about a bunch of times about, when Bartek, when you talk about AI hype, right? There's a lot of BS usage of AI these days because it's all hype, right? These are the ones that fascinate me because I'm like, these are actually really, really good. These are really, really helpful because it's taking where, it's way too complicated or complex for somebody to set up a system to do and say, all right, let's give, if we go back even to the old, the goat analogy, I don't know if you know the goat analogy. It was people were using goats to clear fields, right? And this is like maybe within the last 10 years or something. And people who do lawn services like, oh my gosh, these goats are going to put us out of business. And it's like, no, the goats aren't going to put you out of business because you're much more efficient, right? So it's the idea that which is the most efficient way to do it, that's the one that's going to win. And if you're already efficient, you'll be fine. If you're not, it's going to be the new thing. But the goats aren't going to be more efficient, so don't worry about the goats. In this case, we have even better than lawnmowers, right?
Yeah, that's the interesting analogy. I've never heard about it, but I think it's really good.
Cool. So steady state is really understanding your current system, understanding what type of patterns that emerge in your distributed system will potentially lead to a problem. So really understanding what is normal and what leads to abnormal situations. So that's a steady state phase. By the way, if you're okay, you have also had this obviously in your slides in Cloud Native Austria. We'll try to exactly find the link to that time stamp where you presented on these cycles, because I think that's a really useful visualization that you used. Steady state, what comes next? Hypothesis, I believe.
Yeah, the next one is hypothesis. But before I jump into hypothesis directly, I want to jump into verify. And there is one reason, because it's very similar to what we have in case of steady state. It's also about finding patterns and classification. So basically, if you think about verify and verifying results of your experiment, where you can apply artificial intelligence it can help you to compare test results against expected behavior. And again, you can do that in the context of all the data from the past. So you can feed your model with any data that you have already, and then you can just ask, hey, give me a classification, highlight the deviations and things like that. So again, this is about using the fact that AI is really good at finding patterns, classification, stuff like that. So this is why I want to jump directly into this verify stage, because those two are connected conceptually if we think about using AI. So that's what I really wanted to highlight here. But let's get back to hypothesis, because that was actually the question. So this is, again, it's a beauty and of how AI can analyze a large set of data. So if you can think about the application stack, and I'm going to be talking here, let's say, about Kubernetes stack, because usually when we have some Kubernetes-based enterprise system, it's usually pretty complex. There are a lot of pods there. There are plenty of services running inside. And let's imagine that we have a stack like that with plenty of deployments, plenty of pods. And if you want to chaos test it properly, you actually need to understand the architecture, and you have to design those test cases depending on the nature of service. And you have plenty of services in the cluster, let's say. So if you want to cover this as an engineer, you need to run hundreds of tests, hundreds of iterations. You need to talk with different service teams. There's additional costs with that. And even though you can miss edge cases. Now, let's imagine that you can actually do the same automatically. And there are different tools like that help with analyzing either architecture of the system or running deployment and the entire cluster to actually be able to produce hypotheses for different services that are running inside this cluster, which can then be used for running specific experiments. So let's imagine that you have a design of an architecture of your system. That can be one source of the data for AI model, so it can analyze it. You can have some kind of documentation, requirements, plus running deployment. All of that analyzed by AI can produce hypotheses targeting specific edge use cases for every single service. And then this is an entry point for the experiment.
So to make this a little bit more real, a hypothesis could mean I analyze my architectural diagram, or I analyze distributed traces from my live application. The AI could say, hey, in your architecture, you have a weak point because 90% of your transactions rely on a central service that runs on a single host that has no no failover. This is a clear thing. We need to figure out if this is resilient. And so the hypothesis is if you're bringing chaos into the system, it could be that probably the system breaks, or the other way. I think the chaos engineering is always trying to test something positive. At least I hope so, right? We have this system and we are bringing chaos, and we believe because it is set up that way, even though it's a central component, it will then automatically scale up with high load. It will Kubernetes will figure out how to divert the traffic. So are these some of the realistic use cases? What is a hypothesis? What will fall out of it? What would be?
Yeah, so what you just described is exactly what we are looking for here. Yeah, we are looking for weak spots and analyzing enterprise system where you have multiple services. You can easily miss those edge cases, miss those things that you just mentioned. Mm-hmm. Now, the trust in the way how AI is doing analysis is that it won't miss those spots. It's going to actually be very clear with pointing those weak spots that we can target with our experiment. And we have tools like that out there, actually, especially when we're talking about Kubernetes. I don't want to advertise anything here, but I believe this is an open source project. So, for example, there is a framework called Kraken that you can use for chaos engineering in context of Kubernetes. What is a good add-on to this framework is something that is called Chaos Recommender. So it's doing exactly what I just described. It's analyzing the Kubernetes cluster, it's analyzing pods, and it's looking for weak spots. That's one of the examples of the framework that you can use. The another one, it's called Chaos Eater. This one is also, I think, open source, if I recall correctly. Again, in the context of Kubernetes cluster, it is introducing AI in every single stage of experiment. So it can generate hypotheses, but it also actually can do analysis, can do post-processing, and everything that you can do during experiment using LLM agents under the hood.
Mm-hmm. Yeah, and this is one of the topics I thought was interesting, because I think, especially going back to the idea of the first step of steady state, right? At least where we're at now, I think, I don't want to say a danger, but a caution of the AI in the hypothesis is it's only going to be able to test for what it knows, right? So if your inputs are bad, right? We work in observability, and we see all the time people only put observability into certain areas, only the areas maybe they can afford to, or maybe they have a mix of tools and getting it all in, right? So that's going to impact the data that the AI has to create a hypothesis with, right? So if it's blind to a certain area, it's not going to be able to account for that. But on the flip side, I completely agree. If you do have a data set, it's going to be fantastic at finding those real edge cases. I don't know. I'm curious, let's assume you had complete coverage and complete visibility into everything. So the AI had all visibility. We know in the earlier days of chaos testing, some of the hypotheses were, well, what if somebody trips over a power cable in the data center? Right? How are you going to detect that? Now, I don't know if those are still done, right? I don't know if it's still valid, but I think there is definitely a blend of automation testing versus human-generated chaos. Do you foresee it always being, okay, we have the AI to do a bunch of all the really cool, crazy edge cases like that, but we should also still have people thinking even further of things that the AI wouldn't even consider, like the tripping over the cable kind of thing, to work in tandem as it goes? Or do you see it possibly just all AI completely?
I think that you made a great point mentioning that the data and the quality of the data that you use for training a model is the key part here. So the better data we provide, obviously, the more precise answers we're going to get and more reliable ones. So that's I think the key point. Now, if we're going to assume the scenario that you mentioned, that you have all the data that you can possibly get about the specific system, I strongly believe that still the human touch is really needed. AI won't be able to provide all the possible scenarios. I don't believe that it's ever going to happen, to be honest. And I still believe that the person in, like, when you have a model, and when you're using AI model to any IT area, it can be chaos engineering, or something else. What is really necessary is this feedback loop that you have. So the model is generating some answer, but then this answer always needs to be somehow validated by the person. And this should be like a constant thing. So human being a part of this feedback loop is a crucial thing, also in the context of chaos engineering. So the tandem that you mentioned, I think this is the way to go.
Right. So it's more like we free up the humans from doing the more mundane ones of trying to find all that other stuff, so they can really focus on verifying that the AI's got everything that it needs, and also getting into the more creative, outside the box kind of thing. So it's not a full replace, but it's give the regular, or let's give the less, let's give the tedious work to the AI to do.
Yeah.
And well, just like if you think about, machines in a factory, you still need people in there to repair them, make sure the stuff's coming out fine and all, also do other things that the machines can't do. So it's just changing the role of the chaos engineer, but they're still part of that. But they don't have to do the actual, as much of the dirty work themselves.
Yeah, exactly. And I can give you a good example, which is kind of outside of the chaos engineering space, but this is something from the field. So let's imagine that you have some kind of system that is scanning, Docker images and finding vulnerabilities. And there are different tools that are reporting that kind of vulnerabilities out there that you can use. One common thing that is happening is that plenty of those vulnerabilities are actually false positives because of different reasons and the way how those scanners works. And if you get a list of those vulnerabilities, you can assign it to an engineer owning this image to verify if those are false positives or not. Now, what if we can train a model that, based on the, let's say, SBOM, for example, generated for this image, or any data that you can provide, can go through this list and give you like initial assessment if the vulnerability can be potentially false positive or not, with the reasoning. Now, how easy is that for the engineer to have a specific suggestion now to verify if what AI produced is valid or not? It's way easier, because if you have the information and the reasoning behind why model decided if this specific vulnerability may be or may not treated as a false positive, it's way easier to go straight to verify this hypothesis that have been provided by artificial intelligence. So this is one of the examples where you still need someone to take a look at the final result, but it's a huge boost of productivity for the entire process.
Yeah, I like that. That's a great example. As you said, while it might be outside of chaos engineering, even though actually I think there is a use case for chaos engineering on this as well, because you could run an experiment where you are deploying vulnerable code and you want to make sure that your observability actually detects that you have vulnerable code deployed.
See, right there, that's the human element of the chaos hypothesis, Andy.
Yeah, exactly. Right. So do you identify how fast can you react to it? When the hypothesis could be, I don't know, we are fixing it in an hour, but maybe you prove through your chaos tests that it's never been identified. Hey, I have another question. Is the idea of the chaos test, so let's assume the hypothesis, we analyze the architecture, we identify if we introduce latency between service A and service B, we assume something will happen, right? Is then the idea that you first run the chaos experiment to really validate your hypothesis that it really fails, and therefore, if it fails, you have to do something. But if it doesn't fail, actually you made a wrong hypothesis. Or is it you find the hypothesis and then you actually improve the system so that when you run the experiment, that nothing will happen? What is the right approach?
Typically, what I follow is actually to make sure if my hypothesis is right or not. So so I just run the experiment, and I'm just observing what is going on. If I was right or not. If I assume that something is going to fail and it's working, I'm happy, of course, in a positive way. But at the same time, I'm becoming suspicious why I was wrong. But
it could be that your model, maybe it could be that you didn't have all the detailed information about the architecture. Maybe the quality of the documentation wasn't good. Right? You mentioned this earlier. The quality of the data is the thing. And whether it's you as a human or an AI makes and creates a hypothesis based on flawed data, this could happen.
Yeah, and of course, one of the reasons why I do that always is exactly what you just said. There might be multiple reasons why I may be wrong, but if I'm wrong in the right way, so everything works after the experiment, even if I assume that something is going to break, it's still less work for me to verify that through experiment than let's say not doing that and trying to fix something that is actually working. Yeah. So that's basically the thing here.
Cool. Awesome. So if I recap, we started with steady state. We want to understand how our system is behaving, what patterns do we have. Very closely related is actually the verify you said, right? Obviously, because it's similar steps. But then because I'm looking, it's easy for me now. I'm looking at your circle with the 5 different stages connected together. So folks, if you listen to this, really check out the presentation, check out the visuals. So steady state, coming up with a hypothesis. AI can definitely help here to come out and identify weak points, maybe in combination with some well-known things. When tripping over the cable is one thing, but we obviously know certain rules, right? If you think about Java-based applications with memory pressure, with garbage collection, I think you can make certain. You don't need an AI. I think it's just like certain rules that we've learned over the years, or the database connection pool sizes, latency. These are all things that typically are weak points in systems. So hypothesis is great. Now running the experiment. What is it? Just a load test that you run, and then you are injecting chaos, like killing pods, or injecting latency, or can we also use AI there to run the experiment?
Yeah. So the main part where I see artificial intelligence can help and speed up productivity in terms of running experiment is actually creating the experiment. And of course, it depends on what kind of framework you're using. Yeah, it can be any framework that you have out there. And I think it's no different than just generating, I would say, a code. So you have a different AI-based tools like Copilot, which can speed up generating the codes that you're actually using to create your service or your product. And it's exactly the same in the context of chaos engineering. And that was the meaning of this slide. So for example, and this is something that we've been talking about during this presentation, if you're using something as simple as AWS fault injection simulator, you can actually use Amazon Bedrock or whatever it is to generate a template that you can just upload to fault injection simulator and just run. That's it. It's no different than generating unit tests using some AI tool for your code. Yeah. So this is exactly what I had in mind when I was talking about running experiments. So it can, the example from my slide. Yeah. You can just go and say introduce 100 millisecond latency on database calls, and you just get a template that you can upload to AWS fault injection simulator and just run. That's it. You don't have to write any code. Yeah. That's the productivity boost that you can get when you're talking about this stage.
Cool. Yeah, and Andy, I would think too, and I don't want to spend much time here because I know we need to get to a couple more, but going back to our old origins, with the load testing, like if you're going to be writing scripts to be running traffic against these systems, this is where I think AI can really help as well. I mean, yeah, I know as old script creators, right, we love to pride ourselves in the complexity of our scripts, but to the same point with AI, even if I go back to LoadRunner from back in the day, it used to have a correlation engine. So you run the script twice and it would look for what changes and it would replace, right? No AI. It was just, but at the same time, if we take the same idea of the inputs for the AI for the chaos, you can point the script generator at the API endpoint. You can point it at all the documentation for the API, all the different kind of inputs and everything, and it could just generate all those scripts for you so that you can then run those a lot quicker and more efficiently in this chaos cycle. So even outside of chaos, the components of building that whole chaos cycle could be used in a lot of ways. And in fact, I wonder if, how much longer script creators will be around, because that seems like an easier one to not necessarily the load design, but the script creation.
Well, even the load design, I would argue, right? Because if an AI gets access to your observability tool where you know how much traffic is coming in, then you can say, create a load profile that covers the peak period in a month. Yeah.
True.
What is the
peak
period? Yeah. So I think that's also all good. Cool.
Yeah, and of course, one important thing here is that I don't believe that AI can generate, full enterprise application. You get again, this is this human in the loop.
Right.
Yeah. Whatever is going to be generated, it's definitely needs to be the review, but that's a boost of productivity again.
Yeah. Very good. Trying to kind of finish that cycle. So steady state hypothesis, running the experiment. Now we're actually at verify, which you said is closely related to steady state. What happens in the verify?
Yeah, so conceptually is really, really close to the idea that we have in steady state. So again, you have some test results that you get from the experiment. You have some expected behavior. You have some data from the past experiments. You can actually use machine learning or any other approach that is backed by AI to classify whatever results you get, to link metrics to causes, highlight deviations, everything automatically based on data. So the most important points can be highlighted. And very often what is happening with after running experiment, when you get all those data, you can also get a lot of noise. Now AI can help with filtering those noise and pointing to those specific most important metrics patterns that you can get after running the experiments. So that's the beauty of finding patterns by AI.
Mm-hmm.
So pretty easy and very connected conceptually to the steady state.
Yeah. Which means we are at the last step of our chaos lifecycle, improving the system. So assuming that we really have our hypothesis confirmed that something breaks, I guess this is now the place to improve your system.
Yeah. So again, if we think about how we can apply AI here, there are a few levels that we can talk about. In the most common case and the easiest to apply is actually, again, to use AI to propose specific targeted improvements in your system. So based on and we're coming back kind of to the hypothesis. So if model knows about architecture, model knows about all the documentation, use cases, deployments, et cetera, based on the results and based on the expected behaviors, it can analyze even repository of your code and can propose specific changes that you can apply to improve. That's the one level. The second level, obviously, because what we're heading with AI is the automation. So the second level is where your system can detect those improvements and can also apply.
Mm-hmm.
Now, let's imagine the situation where you have all of that automated and you constantly and continuously run the experiment, get the results. After getting the results, automatically AI can propose improvements, can apply those improvements to your repository, can rebuild your service, can rerun all the testing, including the same experiment. So you have like a continuous improvement cycle. Of course, in a perfect world without the human intervention, but as we discussed previously, we need someone out there to tackle that entire process. But if you can automatically do all of that, again, it's a huge productivity boost. So there are a couple of levels of how autonomous the entire improvement system can be. There is one use case that I'm also talking about during this presentation because I found it really interesting. It's the idea where you actually have the AI agents running in a specific system, which can fix issues in the system at runtime by, for example, changing configuration of your system. And one of the examples, I have no idea if this is true or not, but I find it fascinating as the example, is the auto remediation agent by Netflix. They call it Nightingale. And again, I don't have any proof that it's true, but the entire concept is really, really great. So there's an agent they have that can apply memory configurations on the fly, depending on how the system behaves, which they say can remediate 56% of all the memory configuration errors, and then can reduce cost at the same time. So, and all of that is based on artificial intelligence, which is analyzing on the fly the patterns, what is going on in the systems. I found it really fascinating in terms of improvement.
Yeah, it's really cool. Brian, this reminds me, and maybe a quick shout out to our friends from Akamas.
That's exactly what I was thinking.
Yeah.
I was going to bring that point up. Yeah, go ahead.
Yeah, because Akamas, right, we had them on the podcast, and they are basically doing continuous performance improvements where they run constant load and then make changes to all the different configuration settings, whether it's in your Kubernetes, in your JVM, in your databases, and basically do goal-based optimization. So they are basically optimizing the system until they reach a certain goal, and the goal could be faster performance, lower memory footprint. They're doing something similar in that area, yeah.
That's really if we just go back to their early days, I know they do a lot more now, but the early days was like how many JVM settings are there? Like a couple hundred, right?
100.
And people know just about a few. So the idea was puts it in there, looks at your observability to see what's going on. It makes a tweak, checks your observability, see if that made anything better, and it just keeps on tweaking until it gets the right state. Again, relying on those inputs for steady state, right? So. The other really cool thing I was thinking about with this whole idea is, listening to, or if you think from the scientific method, right, your goal is not to prove your hypothesis correct, it's to prove your hypothesis wrong, right? When you're going to do an experiment, because proving it correct, you can never prove it correct, but you can prove it that you haven't been able to fail it, right? And if you think about the process of doing that requires multiple different iterations. Okay, the first thing I looked at didn't prove it wrong, but now how many other things do I have to do until I get to a confidence? Like, okay, I'm very confident that I can't prove this wrong. Still doesn't mean it's right, obviously, in the scientific idea, but it just hasn't been proved wrong. The idea of, okay, what happens if our database is out for an hour, right? Many different iterations and many different tests of how that might happen, this and that, right? So that AI is going to speed up all those iterations of how to do that because it's going to know all the different levers it can pull to stop talking to the database for an hour, right? Whereas if it was just human, first of all, you'd have to figure out all the different ways it might go down or all the way communication might be disrupted. So it just really sounds like a really fast-tracked approach to, rapid fire, finding as many paths to try to prove that hypothesis wrong and just firing them over and over and over again until you do, right?
Yeah, and this is exactly what it's all about. And in the end, as we said a couple of times, we need a human looking at the entire process. But there is one thing that I'm always talking about when I'm describing a mission and vision of my organization, is that we want equality at speed, which means that you have to automate. And now having artificial intelligence we can actually do that, because in the past there were lots of areas that you couldn't automate. Really, you need to really have a person doing all that tedious work instead of the same person doing creative stuff. Right now, you can actually use artificial intelligence and improve most of those areas. So that's the beauty.
Right. It's all about efficiency. Why have a human, or even why have a human rack a server when you can spin up a pod, right? This goes into the AI stuff. Like, why have a human do any of that stuff if you can put that stuff onto the AI and have the humans do the pieces they need? One last thing I wanted to get in there, Andy, was Bartek, you had mentioned all the different inputs for the after validation. The step is called what? Like not remediation, but what's the step after validation called?
Improvement,
right? And one thing you said in the beginning, which I thought was really fascinating, Andy, but it didn't come up when you said this other part, is requirements, right? So in terms of the improvement, right, if the AI has access to not only what our goal is for speed and all this, but maybe we only want to spend, so much on our infrastructure to run this component. Maybe this component has to be responding within a certain amount of time. Like if you're rolling out a new release, or not necessarily new, but what are the requirements for some of these pieces so that we know from a business point they're successful, including cost and all that, right? Because if the remediation is, hey, we have to throw, another 100 virtual CPUs at the problem, right? That might not be the good remediation, right? So by adding those requirements, as you mentioned earlier, the AI is going to put that all in mind and be finding a solution that fits into all those aspects of it, the business side as well as the technical side.
That's true. That's correct. That's one of the reasons why I mentioned requirements, because exactly because of how you just described it. Overall, the software that we write is running some kind of business, and this is what the business is looking for. For making sure that that any requirements that the specific system is having and the requirements that our clients are looking for are fulfilled. So that's exactly what AI can take into consideration during any experiment that we can run.
Unfortunately, time is up, because it's amazing how time flies when we speak about topics and when we all have guests that are especially working in the area where we have our background, which is around quality and about performance testing. I can just encourage everyone, check out your talks. We'll link to one or two talks that you gave recently, especially the one to Cloud Native Austria. Also, Bartek, if you're okay, I will share the LinkedIn profile from you so people can also connect and follow up. I'm sure now that we are connected, I'm pretty sure we'll cross paths anyway. And if there's anything coming up, if AI is going to make some additional leaps in the future that will make the life of engineers even easier, then we're happy to have you back for another episode.
Yeah, of course. Sounds great. And, thank you for having a great discussion today.
Yeah, it was amazing. And I can't wait to see, my last thought on this all is, as people start incorporating AI into more parts of their architecture, right? I don't mean in the chaos cycle, but in their actual deployment, messing with the AI is going to have to be part of chaos test as well. So you're going to have AI trying to mess up the other AIs that are running in the system. So it's just this fun. Yeah, this stuff can go on forever. It's amazing, though. Thank you so much, Bartek, for being on. I wonder if AI gets as excited when it learns this kind of stuff like we do. But for Andy and I, chaos testing or chaos engineering has always been, as we've been exploring it, it was fascinating, especially for me, coming again from the old, performance and load testing side, where it was not quite, it was this grand extension to what we were trying to do in performance testing, or not even, trying to simulate a load, see if the system fails, and then this broader, most really amazing field of chaos engineering on top of that. And then add this AI stuff into the cycles, it just reinvigorates the really coolness of chaos engineering. So look forward to seeing what comes with it, and I hope everybody enjoyed today's episode. So thanks again, Bartek, and Andy, thank you. Bring it on.
Thank you.
Bye-bye.